Thank you for this flattering introduction. It is a pleasure to be here. I understand that this crowd is a crowd that is hard to please because there are world experts in exactly this field. And there are also people that are completely foreign to this field. There are world experts, but on different things. So I'll try to have something in for everybody, but not everything, of course. So what's the context? Cosmology over the past 20 years has made a transition to what is called precision cosmology. It has moved from a data-starved science to a data-driven science and has now a standard model. The standard cosmological model needs only a few parameters to describe origin, composition, and evolution of the universe. That is, explain how it was born and how it came to look the way we look at it today. But there is a big difference between modeling and understanding. And towards the end of my talk, I will come to this. So how can we date so precisely the beginning of precision cosmology? And so to understand this, we just need to read that the dedication of the Nobel Prize in Physics from 2006, which was given to the 2 PI of the 2 instruments on the COBE satellite. And this is the image released in 92 and then published in 94 of what has been called the primordial fireball, the infant universe, and for aficionados, the cosmic microwave background of, from now on, CMB. So what they say in the dedication is that this result provides increased support for the Big Bang scenario for the origin of the universe. This measurement marked the inception of cosmology as a precise science. So before we go on, what is cosmology? So cosmology is the study of the entire universe. For cosmologists, galaxies are just points. So we are really looking at enormous scales. And so if we don't work in this field, we have to sort of try to wrap our mind around these scales and this type of concept. Okay, so what is this? Well, this is our own galaxy, but what we are interested in are these patches. These patches are tiny temperature fluctuations that are seen in the radio part of the spectrum. So today we know, thanks to the work of many, Slipher, Hubble, Alper, Gamma, Herman, etc., that the universe is expanding and has been expanding over the entire history. And we know that it was born in a hot Big Bang. It's even a title of a successful television series, so I don't have to say anything more about this. And the other bit of information that we need to know is that looking far away is looking back in time, because we see thanks to light, and light travels at a finite speed. And for cosmology, looking far away, it's looking at high redshift. It's simply because the universe is expanding thanks to the Doppler effect, light is being redshifted, and so we can directly connect distance, time, and something that is observable, redshift. And also this means that there is one visible universe. We can only receive information from where light could have traveled to us. So if the universe has a finite age, inevitably we can only see up to the edge of the visible universe. And so this introduces the concept of horizon. But it gets more interesting. So this is a sketch of the expanding universe. We are here. When we look far away, we look back in time. And then if we actually look at the electromagnetic spectrum, at light, you can only see up to here. Then beyond that, you can't see with light. You could see with something else, in neutrinos or in gravitational waves, but you cannot see with light, basically because this is called recombination. So the universe was opaque before then and became transparent after that. And so that's why you can't see beyond. It's like looking at the sky on a cloudy day, you see the surface of the clouds. So the same kind of physics goes on in here. And the image that COBE gave us is the image of the universe back here when it was only 300,000 years old. So some quick history of the cosmic microwave background temperature measurement. In 1965, there was the Nobel Prize for Penzias and Wilson, who saw this uniform glow, telling us that indeed there was a hot Big Bang. Later, the Doppler shift due to the fact that our own galaxy, the Milky Way, is moving through space, was seen, but only in 1992, some non-uniformity in this primordial fireball was observed, and then only about 1 part in 10 to the 5. So why are these non-uniformity really important? Well, they're important because today we know the universe is not homogeneous. There are galaxies, planets, us. And if they were created by gravity, by the gravitational attraction of gravity, there must have been some seeds at the very beginning. And these are those seeds. So what does this mean? This basically means, in other words, that in the early 1990s, for the first time, if this is again a schematic of the expanding universe with the Big Bang here and us here, we could see both the final product. This is, well, the rendition, it's a bit sketchy here. Each point represents a galaxy, and it's a cone because it's a galaxy survey. The telescope sees a patch of the sky, and then since I can't plot in 3 dimensions, this is a slice that has been projected on the plane of the projection, and this is the distance or redshift. So in the early 90s, we could see the final product, but also the initial conditions. And so you can learn a lot by trying to make the connection between here and here. In other words, if the universe was a person of, say, 50 years old today, this is seen here. By looking at it here, it will be looking at the person when it was only a couple of hours old. So you can learn a lot about this person if you have these 2 different snapshots. Okay, so in the early 1990s, we saw this. And then there were other measurements, both ground-based and balloon-based, and an avalanche of data arrived. One of the milestones in this avalanche of data was the WMAP satellite, the NASA satellite WMAP, on which Analysis High was involved, which is much higher resolution than COBE, full sky map of the primordial fireball. But that's not the only one. When I say avalanche of data, it really means that there were many, many, many experiments in trying to measure the cosmic microwave background with higher resolution. So up to now, we have 3 satellite full sky measurement, the COBE one, which we discussed already, the WMAP, which we've been introducing right now, and now I should introduce the Planck satellite, a NASA ESA satellite mission with a heavy Italian involvement, also many people that play a fundamental and crucial role in getting these things to be a success are here and are in SISSA and are in this room. And also ground-based experiment, not full sky, but better resolution, and among them the South Pole Telescope and the Atacama Cosmology Telescope. And so let me show you again figuratively the transition between low resolution, better resolution, and much better resolution here. So again, in the early 90s, we have this. Let's also not forget the announcement of the accelerating universe in 1998, 1999, that then received the Nobel Prize in Physics in 2011. So putting together all these pieces of information, a model emerged. But it was more like qualitative way of thinking. And since then, an avalanche of data arrived. And so into the first decade of the new century, we had much higher resolution maps of the primordial fireball. And much better mapping of the galaxy distribution more nearby. So this is an example taken from the Sloan Digital Sky survey. Now you see that there are two cones because you want to look outside our own galaxy, so you look in the north galactic plane and the south galactic plane. Each of these dots represent a galaxy. The previous survey that I show you would have fit in this little corner here. And there is also much extra information here because you see colors, but colors simply represent that there are much more information about the galaxy, not just the position, but more information about the object. And it's the detailed statistical properties of this report that go from here to there that tell us a lot about the universe. And now I have to remind myself to introduce some other concept. Whatever cosmological model will not tell you that particular galaxy is going to form there and that particular planet is going to form there. Basically, if we think about it, it's because we are very ambitious and we want to know something about the entire universe, but what we can see is only the visible part of the universe. And so we are dealing with something that is inherently statistical. And so what the theory can tell you are the statistical properties of the universe as we see, not the actual deterministic properties. And so this information is usually compressed in what is called an angular power spectrum. And for the mathematicians among you, you will jump on your chair because you can only fully, in a lossless way, compress this information if the field is a Gaussian random field. But we have some very good both theoretical and experimental indication that to a very good approximation, this is a Gaussian random field, so this compression is almost lossless. Okay, so the model that started to take shape in the early 90s, it's a model that has survived this avalanche of data well into the first decade of the year 2000. What is this model? This model has very few parameters. There are some parameters that describe the smooth universe and some parameters that describe the fluctuations. The smooth universe describes basically the background expansion history, and these parameters are the amount of matter that there is, and indications say that there are both baryon, which is matter like we know and love, and also some other component, which is still matter, but is called cold dark matter, and there is a big area of physics that is actually devoted to trying to get to see this cold dark matter, but for cosmologists it's just one parameter. You can put it in there because it's physically motivated by particle physics, and also because there are some observation that says that you would need something like that to create structure, and then see how much of it you need to actually fit the observations. Some Einsteins hated and loved the cosmological constant to explain the accelerated expansion of the universe that was seen in 1998, the current expansion rate of the universe, and some other parameters that basically describe our poor understanding of physics dealing with how do a star switch on, how do a galaxy switches on. And then there are some parameters describing the fluctuation, as I say, only statistical properties, not that galaxy is going to form there, and therefore we describe the power spectrum with an amplitude and a power spectrum slope, and then if you want to be ambitious, something that we're going to come back to later on if we have some time. So this is the extremely successful standard model for cosmology called LCDM or lambda CDM, where lambda stands for Einstein cosmological constant, CDM stands for cold dark matter. This extremely successful model was formulated in the 90s, but then survived this avalanche of data. And before I go on, we need to understand this other concept. We only have one observable universe, and this is the course for cosmology, because we can only make observation and only of the observable universe, not experiment. This is not like going in a lab and being able to poke your own universe and see how it responds. So we fit models to the observation. Fitting model means constraining numerical value of a bunch of parameters to describe the model. So any statement is model dependent. And this is the course of cosmology. Also, what the aficionado call gastrophysics, that is, nonlinearity gets in the way. There is a lot of very complicated physics that goes on in explaining how galaxies form, how something shines, and most of the information we get from the universe comes from light. Also, those fluctuations that we've seen, very small, 1 part in 10 to the 5 in the primordial fireball today, are highly nonlinear. And as you know, describing nonlinear evolution, it's complicated. So different observations are more or less trustable. But it's, however, somewhat of a question of personal taste. Decide which observation you want to trust more. So think about the standards of poor credit rating for countries. So results in cosmology will depend not only on the model you choose, but also on the data you are willing to consider. Now, I personally try to use only better than A rating, but this is a question of personal taste. However, this is also a blessing. This is also a blessing because in principle, since we have only one observable universe, we can observe all there is to see. And the cool thing is that technology is actually getting us there. So let's go back to the era of precision cosmology. This standard model for cosmology, these few parameters that describe the universe composition and evolution, means that these few parameters are known to present precision. However, measuring parameters doesn't necessarily mean understanding. So for example, what is the cosmological constant? What is the cold dark matter? Where do they come from? And regarding the perturbations, is there a mechanism that set out this initial perturbation that lay them down there and then, say, grow and generate galaxies, planets, and us? And as the Daily News claim, 96% of the universe is missing. We haven't seen cold dark matter and don't really understand what is lambda. So maybe for aficionados, I'd like to show this plot. In this plot, we are here, and we go back in time towards the Big Bang, and there is also the energy scale of the universe then. And when something happens, generation of primordial perturbation, cosmic microwave background, us. And then there is some color scheme. So white means well understood, and darkness means that it's proportional to poor understanding. So today, the universe is dominated by dark matter and dark energy or cosmological constants, so there's a lot of black and there's a lot we don't understand. There is a chunk during the life of the universe where the universe was dominated by radiation and where the physics was linear, very simple, was just atomic physics and was very well understood. So this is white. Luckily, when we look at the cosmic microwave background, we look here where there is still quite a bit of white. So we have quite a good understanding of what's going on. But of course, if you're curious, the name of the game is to try to understand what goes on here towards the beginning of the universe, also because there are very high energies involved, the kind of energy that you will never be able to test with an accelerator on Earth. And so you can see how there may be an interplay between high energy physics and cosmology in here. And this is one of the many areas of interplay between the two fields. So let me show you an image of, again, the cosmic microwave background by the WMAP satellite. These cold and cold spots represent a tiny ripple in density, and those are the seeds of galaxies. And so, as I say, the detailed statistical property of these ripples tell us a lot about the universe. Let me see if I can explain you in few words, no equation, how is that? So the universe back then was made of a very hot and dense gas. Think about taking the universe today and compressing it back, running the movie of the expansion of the universe backwards. So it was emitting radiation like anything that is hot and dense. This is the radiation we see when we look at the cosmic microwave background. this radiation is uniform but with tiny density and temperature ripples. So we are talking about ripples in a gas. These are sound waves. So this has been called a cosmic symphony because we are basically seeing sounds. And this is tiny fluctuation that give rise to the galaxy. So when Fermi was trying to explain to people the first particle accelerators, he was saying, well, you know, it's like to take two grand piano, smash them one against the other, see all the pieces that come out, and try to understand how the grand piano is made and while it makes music. In this case, we're trying to listen to the sound and figure out how the instrument is made. And this is not silly. If you think about it, you know, you knock different material, and you can guess what is the material depending on how they sound where you knock them. So it's a similar kind of thing. And the other bit of information you need is that if it is true that the universe has a finite age, and then there is a fundamental scales, because any kind of information could travel only as fast as light, and therefore only as far as the speed of light times the age of the universe. And so this gives a fundamental mode, and as you know in any instrument, when a string, you perturb the string, you get a fundamental mode and you get overtones, like blowing on a pipe. So when we look at the last scattering surface, remember the analogy to the surface of the cloud, we are seeing a snapshot of this plasma, of this photon baryon fluid. And it's actually a plasma. A lot of the first people that study the cosmic microwave background were plasma physicists that study bombs. It's plasma. On larger scales, we are seeing primordial ripples, and you can ask who or what put them there. And then on smaller scales, there are two competing physical effects. There are the photons that create radiation pressure, and there are gravity that create compression. So this is what set up the sound waves. And of course, the sound waves stop oscillating on recombination when the universe becomes transparent because it cools down, and then the photons travel to you. And so you get a snapshot of this photon baryon fluid. And of course, the horizon size at the last scattering surface gives you your fundamental tones and overtones. Can we see those? Yes, these are being seen. And now here, I'm showing you the plot from, again, the WMAP 9-year results, and I didn't show the Planck results were announced in March this year, just because those data are so much better that then I wouldn't be able to easily zoom in this part, which is what I want to show you right now. So we have to use the low-resolution data to actually see the physical process that I want to show you. So this is what I was describing you, and so you can see down here, large scales, primordial fluctuation, these fundamental modes, and these overtones. We are thinking in Fourier space here. So different compositions of the universe, or tiny different value of the cosmological parameter in the cosmological model, would actually give much worse agreement to this data point than this line, which is the one that is predictable from this model. So at this point, I think it's good to look at the conclusions that were written now 10 years ago from the WMAP cosmological parameters paper. Now, I don't want you to read over through this, but reading it 10 years later, I found it particularly interesting. So it said the cosmology has now a standard model. It says what are these parameters there that are measured very well. So cosmology is in a similar stage in its intellectual development to particle physics 3 decades ago, when particle physicists converged to the current standard model. The particle physics model fits a wide range of data, but does not answer many fundamental questions. And over the past 3 decades, precision tests have confirmed the standard model of particle physics and searched for signature of natural extension of the standard model, supersymmetry. Now today we know that in 2010 we haven't seen supersymmetry, but at least the Higgs was seen. Now for cosmology, it says that over the coming year, improving cosmic background and large scale structure data will provide more rigorous tests of this model and search for deviations from it. And this is indeed what actually has happened. So why would we look for deviation from the standard model? Well, because it's nice to test the physics on which the model is based and beyond it. So what is this cosmological constant of dark energy? What is the nature of the initial condition? Neutrino properties can give some imprints into the cosmos, and also beyond the standard model physics. Note here that there is no direct mention to dark matter. If I would ever to show this slide to a cosmologist, they will be perfectly fine with it. But of course, if I show this slide to anybody else, he said, well, you have a lot of cold dark matter there. We haven't seen it. Why you don't worry about it? And my reading of this is that cosmologists understand that dark matter, at least it behaves like matter, and then it's somebody else's job to actually find it, maybe with some direct detection experiment. There is some hope to understand some properties of the dark matter by looking up the sky, but it will be very difficult to actually, I've seen a neutralino, here it is. On the other hand, all these properties can be addressed almost exclusively by looking up the sky. So that's why cosmologists will not be worried about this big omission here. So, okay. So now let me come to the Planck release, the data that were released this spring. So you see another full sky map with much higher resolution. And so again, we play the game of compressing the information, and look how beautiful this is. But I have to change from a logarithmic scale to a linear scale, so otherwise you don't see how much more information there is in there. But what I want to do is I want to show you the following. So this lambda CDM model makes very precise prediction. I can take the old data and just say, within the lambda CDM model, what is the 68 confidence prediction on scales that are much smaller than the one that I have observed? Since I have a model, I can do that, and that's a great region. And then you can put on top this ground-based experiment, and they seem to align quite nicely. And then you put on top the Planck data, and again, it agrees very well. If the model was wrong, it would be difficult to actually predict observation that you haven't seen, you haven't done yet. And there is also another that I find impressive measurement, which is from the detailed statistical properties of this map, and in particular for the mathematician among you, the tiny deviation from Gaussianity of this map. There's a way to reconstruct some information about all the foreground structure between you and the last scattering surface, thanks to the effect of gravitational lensing, which again was predicted by Einstein due to the fact that stuff bends space-time, and there is stuff which is clustered between you and the last scattering surface. And again, this is the lambda CDM, and these are the data. I found this amazing. So really, there is a wonderful agreement of new data with the lambda CDM model. So now, what everybody is talking about. So far, if we consider figuratively this fresco from Florence Duomo, we have talked about this bit. You see, everybody is happy and smiling. But if you look down and dig deep, they find very strange monster lurking beneath. So what is everybody talking about? Well, if you squint, you will see that on these scales, the prediction seems to lie a little bit above what was actually measured with subsequent data. If we're talking about precision cosmology, should we worry about this? Everybody talks about cosmic recipe adjustment. Maybe if you're sitting in the back, you wouldn't see any difference between the cosmic recipe before Planck and the cosmic recipe after Planck. But this is precision cosmology at play. Even for a plot like that, you have to squint, and the differences are large enough, even though they are at the percent level, that worry cosmologists. There's another thing that we've tried to, which is go along this line, that we work with my collaborator and I, which is the importance of local measurements. There are some quantities that are parameters of the lambda CDM model that you can actually measure directly without any dependence of the model. And these are, for example, the local expansion rate of the universe, which is the Hubble constant, and there is another parameter, which is the age of the universe, which you can derive within the Landau-CDM model from the cosmic microwave background data. So what I say, it's a little bit, we're going to play a game now, which is a little bit like shooting at a target from the other side of the universe. So the cosmic microwave background with the Landau-CDM model, which is at, when the universe was 300,000 years old, is trying to shoot at a target that is predict the value of the Hubble constant and the value of the age of the universe today, on the other side of the universe, literally. And so that's the target, because these are local measurements which are independent on the cosmological model. And this is your aim, because this is cosmological model dependent. So these are the constraints from the previous WMAP experiment, and these are the constraints from the Planck experiment. Is this having a good aim or not? Before precision cosmology would say, this is great. But precision cosmology means that you do worry about this small mismatch. And you can actually try to quantify this. We came up with a statistical way to quantify that. And it boils down that the odds of this measurement and this prediction being drawn from the same model are 1 in 53. Whether you want to worry about 1 chance in 53 is up to you. But at least we can quantify that. So you can go the way of blaming the data, and illustrious people have gone this way. For example, you can say, well, maybe the local determination of the Hubble constant, of the expansion rate of the universe today, is wrong. There are some systematic effects. Saying precision cosmology doesn't mean saying accuracy cosmology. And there's a big difference between precision and accuracy. But also you can go another way and say, is there any model extension that fixes this? Maybe the Landau-CDM model is incomplete. Actually, we know it's incomplete. And later on, I'm going to say why we know it's incomplete. So we went through and we actually conclude that 2 large neutrino masses will make this deviation really too bad. You don't want to go there. A little bit extra effective number of neutrino species, like if there was a sterile neutrino, would actually reduce this tension. However, there are other data out there of the universe between the local universe and the same, well, there's almost the entire universe between these 2 snapshots, so there's a lot to be observed, does not really support this interpretation. Or you can say, well, maybe the cosmological constant is not a cosmological constant, it's something weirder, with an equation of state parameter, which is pressure over density, which is less than -1. That means it's really weird. -1 at least is vacuum energy, less than -1, who knows what the heck that is. Will make this tension not significant, but whether this is a palatable option, that's up to you to decide. But roughly speaking, if we forget about the local determination of the Hubble parameter, the Landau-CDM remains a very good fit to the universe. These data points are not, the line is not a fit to the data point. The data points were from 2010 measurement of the large scale structure power spectrum. That is how galaxies are clustered in the nearby universe. And the blue line is the Planck best fit Landau-CDM model extrapolated to this. So the line is not a fit to the data point, but is an extrapolation within a model. So that's 13 billion years of gravitational evolution within that model gets you exactly on top of the data point. So where do you go next? Well, I would say that the next step, and which is already going on, is exploring the lower redshift universe. So we've seen these from Planck, and these are the seeds of galaxy formation. We now have powerful computers for which we can actually put this initial condition in a box, play God, and just tell where the distribution of stuff in the universe is going to be, again, statistically, after 10 billion years of gravitational evolution. And then we have direct observations of the clustering properties of galaxies of many shapes and sizes around us. So the motivation to go and look at the lower redshift universe is, well, that the cosmic microwave background primary temperature it's basically all done. We have done the ultimate experiment. I told you that technology has brought cosmology to the point that can make ultimate experiment, can observe all there is to observe. And for the cosmic microwave background primary temperature, we have reached that point. That's done. There's more information in the cosmic microwave background temperature, yes. But this information is coming from everything between you and the last scattering surface, so it's called secondary, not primary. But the primary, it's done. There are three main open issues in cosmology: dark matter, cosmic acceleration, and origin of perturbation, and a lot of information in the lower redshift universe. It is in the lower redshift universe where we have the technical capability in the next 10 years or 15 years to perform an ultimate experiment. Of course, there is another door that waits for us to actually open, which is the door of the cosmic microwave background polarization. The light from the cosmic microwave background is polarized, and there is a rich amount of information in the polarization, and only part of it, a tiny part of it, has been harvested. I don't know if I will have time to mention this, but so that's why I want to say something here. So the two big open questions in cosmology: what is dark energy and what is the physics behind inflation? That is what set out those initial perturbations that we've seen there. And the two big questions have common aspect. They both involve a period of accelerated expansion, and they both ultimately will be solved by looking up at the sky. So, with the cosmic microwave, with the CMB, we were very successful because we could actually interpret very simple physics, the baryonic acoustic oscillation, those peaks that we've seen in the power spectrum, and those tell us a lot about the universe. Can we play the same game in the lower redshift universe? So the cosmic microwave background gives us like a fingerprint of the universe. Is there a signature of this fingerprint in the later universe? And the answer is yes, there is. It's tiny, but it's there. So remember, we discussed this characteristic scale, because information can travel faster than light, and so this fundamental mode corresponds to a specific scale. The same fundamental mode should be there in the distribution of galaxies, because the cosmic microwave background is the seeds of galaxies, so the same information should be enclosed there. And these are called baryon acoustic oscillation. For the aficionados, what we are seeing is the sound horizon at the coupling. For the non-aficionado, is these fundamental modes that we described before. And so this wiggles here. And the idea, but even better if you see it here. So what's the physics behind it? If you have a single perturbation, now the universe is a superposition of perturbation, but at the beginning you have baryon, photons, and cold dark matter that get perturbed all at the same time. But remember, photons, free streams, while photons are coupled to the baryons, they go away and they carry the baryon with them. When the universe becomes transparent, the photons and the baryons decouple, and then the photons keep running, and the baryons stays there. But by now, the baryons are offset with respect to the cold dark matter. So let me see if I can run it again. So here's photons and baryons, and then they decouple, the photons run away, and the baryons remain there. But now the dark matter says, ooh, there is an overdensity there, and the baryons say, ooh, there is another overdensity there. And so as time passes, they match each other. So in other words, in the galaxy distribution, I should see this characteristic scale there. So there are many surveys that have detected and are going after this signature, and I want to mention one of them just because we're involved in my own institution with my group, and this is called the Sloan Digital Sky Survey. Sloan is, of course, the person that gave a lot of money to actually build the telescope. Baryon Oscillation Survey. It's a 2.5 meters telescope in New Mexico. It does photometry and spectroscopy. In the SDSS, data were used by now by other 5,000 referees paper, but in this survey there's much more than just looking for baryon acoustic oscillation. And so one part of this effort is the Baryon oscillation spectroscopic survey. It's a 1,000 fiber spectrograph, 2 million spectra, and also quasars. And so the last data release that is available to the public is DR9, but I think Monday, DR10 and DR11 are coming out with new data. I can't show that yet because we can't until the collaboration make it public. But it gets you an idea of what I'm talking about. So as I was saying, these fundamental modes and overtone that we see here can be seen in the distribution of galaxies, and this is actually data with the prediction for the lambda CDM model. Now, notice that while for the cosmic Mercury background I can just show you the power spectrum as it is, for the galaxies I had to show you the power spectrum divided by a smooth one without these oscillations. Why is that? It's because in the cosmic Mercury background, by seeing the photon, I'm seeing where the baryons are. In the galaxies, since there is only 1/7 of baryon done cold dark matter, and what I'm basically seeing is where the cold dark matter is, this signal is reduced by a lot, because the signal is created by only 7% of the whole thing. And that's why I need to divide by a smooth component for you to be able to see it. So the signal is much, much, much smaller, but it's there. Of course, this survey were designed to look for this signature, but there is much, much more cosmological information there. So for example, the shape, the full shape of the power spectrum carry a lot of information. So to match visually what you saw in the cosmic Mercury background and what you see in the larger scale structure, we can do it this way. And the fact that we are looking for this tiny thing. So that's why it's hard to measure. So this is probably for aficionados, so I'm not going to talk through this. Only if you're aficionados, you won't get bored while I tell you figuratively what's going on. So basically now we have a way to look at a fundamental scale, a standard ruler. We have a way of seeing this standard ruler not just on one particular snapshot, which is the cosmic Mercury background, but several different snapshots if we are good enough to observe galaxies that are far away enough and cover enough depth. But even more interesting, remember that Einstein told us that space is not necessarily geometrically flat, and therefore you have all this kind of a geometric effect, and so it's different by looking at a standard ruler in the line of sight direction from looking it in the transversal direction. You can learn a lot about the geometry of your space, time, if you can do both measurements. And this is something that you cannot do in the cosmic Mercury background because you have a single snapshot. But you can do with a galaxy distribution, because in the galaxy distribution you have the entire three-dimensional information. So you can try to disentangle the line of sight distance with the plane of the sky distance. So that's the challenge. And of course there's a lot of more information from the broadband shape, because the broadband shape can tell you about matter radiation equality and can tell you about the property of whatever mechanism that was seeding this initial condition and other subtle effects. Using the broadband shape, however, it's challenging, and one must be beware of many things. Nonlinearities. We see galaxies who inhabit dark matter halos. These are highly nonlinear objects. We don't know how light traces dark matter, and the theory, since it's based on gravity, predicts where all the stuff is, so mostly where the dark matter is. And we observe the third dimension along the line of sight slightly distorted. We can't measure distances directly. Qualitatively, yes, but quantitatively, we measure redshift. And on average, there is a very nice relation between distance and redshift, but on a galaxy-by-galaxy basis, there's a difference because the universe is not uniform, is clumpy, and therefore a galaxy will have a peculiar velocity and tend to fall into the neighbor potential well. Now, there are some ways to try to go around it, and one of the ways, for example, to try to understand bias is to go and look at higher order correlations, not just the power spectrum like it was done on the cosmic Mercury background. This is something that we are trying to do with some people in my group. it's not easy, and let's just say that it takes many years, and not only to our group, but also to competing group, to actually come up with some numbers. And I won't say anything else again, because it's until the collaboration say it's okay to publish, I can't say anything, but we're trying to work on it. So let me go back to the Baryon acoustic oscillation. Here it is, the power spectrum, this power spectrum divided by a smooth function, so you see it much better. And if you want to think in real space rather than in Fourier space, the correlation function, here it is. So this signal is not new. It was predicted in the 1990s, but the realization that actually you could do cosmology with it, it's a 1997 paper. Now, between 1997, when people say, oh yeah, this is cool, we can do cosmology with this signal, to actually detecting it, we had to wait until 2005. And there were 2 papers that came out within a week of each other from 2 competing experiments. However, back then, it was an extremely excruciatingly low signal to noise. And so if you are interested in data analysis, let me just show you these 2 figures from those original papers. The data here are highly correlated, because this is a correlation function. This is the SDSS, and this is the 2DF, the competing survey here. These data are less correlated than this one. Now, if you do data analysis and look at this, you say, well, you are kidding, right? This is, 2.5 sigma, 3 sigma maximum. You can't do cosmology with 3 sigma. You can't measure parameters. You can't say, well, maybe I've seen something. But now there's a whole suite of surveys that are going after it, and the statistical significance is much higher, remember? This and this. So you can really do cosmology with it. Now, I don't want to go into too much detail, but just show this from the Planck cosmological parameters papers, which uses almost the state of the art of this baryonic acoustic oscillation measurement. This is the prediction for some particular combination, which is the information encoded in this larger scale structure acoustic oscillation signature. This is the cosmic microwave background prediction within a lambda CDM model, and these are the data points from several different surveys. So there is a wonderful consistency. Everything is broadly consistent with the lambda CDM model. But the cool thing comes when you try to go away from the lambda CDM model. And so I wanted to just visually see just the blobs of colors, and if you are an aficionado, so you would understand more about this. So in each of these lines, so these are always the same cosmological parameters, and each of these lines, it's one extra parameter that gets added to the base fiducial lambda CDM model. In this case, we make the universe not spatially flat. Remember, Einstein told us there are 3 possible geometries, spatially flat, open or closed, and so you can describe it with some curvature parameter. In this case, you are allowing neutrinos not to be massless, and in this case, you're saying, I don't really know what the dark energy is, whether it's a cosmological constant or something else, so let me allow the equation of state parameter for that thing to be not -1, but something else. And so the red regions are before adding to the cosmic microwave background data, this baryonic acoustic oscillation data, and the blue region are afterwards. So you can really see that it adds a lot of information, especially for some of these parameters. So since my time is almost up, let me look towards the future. So I need to mention Euclid. Euclid is a mission that, it's being funded, and it's it's being developed, of mapping the cosmic web. All the way when the universe was 1/3 of its current size and less than 1/4 of its current age. And the cool thing of Euclid is not only that it will track this baryonic acoustic oscillation all the way here, but also that it will do weak gravitational lensing. That is, it will map again the cosmic web with the Einstein weak gravitational lensing. Now, I'm not an expert of weak gravitational lensing, so I will just mention it so you know it's there, but I would not say more, except to the fact that you can imagine the synergy between looking with high resolution, full 3-dimensional information, distribution of the galaxy, and then having also a lower resolution with the worst 3-dimensional information, but directly of the entire mass. that is in the universe. Of course, you can learn a lot by combining the two observations. And what Euclid promised, it promised error bars of well below percent in this parameter describing the expansion history of the universe. In the next few minutes, I want to say more to come, polarization. So we explored the low redshift universe. We've seen we can learn a lot from it. Let's go back to the cosmic microwave background. I say the cosmic microwave background light is polarized, and there's a lot to be explored there. These are the teasers plot from the Planck collaboration papers. They gave us the plot, but they didn't analyze the data. Well, they haven't analyzed them yet, but they didn't publish the analysis of this data. But just to give you an idea, I tried to plot on top of this figure our current published and analyzed polarization data. And whatever thing I did, I could not, because the error bars are so large that I really had to stretch the figures that we have today for actually making them on the same scale. So whenever there will be a release of the Planck polarization data with an analysis, it will be really, really interesting. So the polarization is the next frontier for cosmic microwave background studies. And this is particularly interesting because, again, it's a very simple, well-understood physics. So if you want to talk not just about precision cosmology, but also accuracy cosmology, it's very nice to rely on extremely well-understood physics. So the polarization was first detected by DAISY, by the DAISY experiment in 2002. This is a W map where these hairlines are the direction of the polarization, smoothed on scales that are much bigger than the scale used for the temperature, just because the polarization signal has a lower signal to noise. So this directly measures the dynamics on the early universe. So far, we've done critical test of the underlying theoretical framework for cosmology, but in the future, we want to ask, how did the universe begin? And maybe we can test the theory of inflation, that is what set up the initial conditions from the universe. So why is the CMB light polarized? Well, it's easy to understand. Temperature quadrupole at the surface of last scattering generates polarization. So if you have uniform temperature, you have a free electron sitting here, and you have photons hitting you this way, you will see no net polarization through Thomson scattering. But if you have potential Hill and potential Wells, then you would see a quadrupolar patterns, and you generate some polarization pattern. So the fact that the CMB was polarized was announced shortly after the CMB discovery by Martin Rees, but it's only after the year 2000 that we can start doing cosmology with it and testing inflation. So polarization has been measured, but it's really important to ask the question, what mechanism generated the primordial perturbation? So before we go on, maybe I should say this. So a polarization pattern is something that is non-local. You can't just say, here in this spot I have something. So polarization, a little bit like electromagnetism, can be decomposed in different modes, electric modes and magnetic modes. The electric modes have no handness, and the magnetic modes do. Scalar perturbation have no handness, and therefore they will generate modes, the polarization modes with no handness. They are called E-modes. Perturbation with handness, like, for example, primordial gravity waves, will generate polarization which has got a B pattern with handiness, like the magnetic field, the B. So we'll generate B modes. So far, we have seen a very nice correlation and anti-correlation between temperature and polarization mode, which is perfectly in agreement with what the basic mechanism for this inflation would actually say you would get. We have seen E-mode polarization, but only on small scale, so these are not primordial ones, but it's still quite interesting. We haven't seen any B-mode polarization, and it's here where we can learn a lot about inflation, because one of the key signatures of something like inflation would be a stochastic background of gravity waves. Gravity waves have handiness, are perturbations that have handiness. If they have handiness, then they will generate this kind of magnetic mode, not just the electric mode. The thing is, this signal, whichever model you consider, is going to be very, very, very small. And so to go after this signal, you need instruments that are much, much more powerful than the one we have today. So what mechanism generated the primordial perturbation? The basically only model we have, it's inflation. And inflation kills 3 birds with 1 stone. It solves the horizon problem. Why is the cosmic microwave background so uniform? Remember, the perturbation are only 1 part in 10 to the 5. Why the universe seems to be spatially so flat? As we say, the flat lambda CDM model explains extremely well the observations. Why is it so flat? And what set up the initial perturbations? So inflation says that there was an accelerated expansion at the beginning of the universe, and that therefore quantum fluctuation got stretched to become classical and super horizon. A little bit like what happened with Hawking radiation at the surface of a black hole. It's just a similar thing. So the shape of the primordial power spectrum encloses information about whatever created this accelerated expansion. We think that it's some field called inflaton, which is potential energy dominated, but the field is rolled down, rolls very slowly down this potential. Then this shape of the inflaton potential is enclosed in this. But the energy scale of inflation is only given by primordial tensor modes amplitude, primordial gravity waves. We can only be seen in the polarization and in the B-mode polarization. So going back to inflation, let me cite David Schramm that says inflation consists on taking few numbers that we don't understand and replacing it with a function that we don't understand. Why is the potential so flat? Where does the potential come from? Why did the field start here? And how do we convert the field energy? It's nevertheless interesting to speculate or try to measure something about the inflation, because these are the windows we have into the primordial universe. This is the physics involved. This is how much after the Big Bang, and this is the epoch. Recombination epoch, 380,000 years after the Big Bang, atomic physics, GR, this is the cosmic microwave background. Nucleosynthesis, 3 minutes is nuclear physics. LHC probes TeV energy, but inflation, which happened on a scale of probably 10 to the minus 30 seconds, probes energies that are between TeV energy and GAP energy, and the Big Bang is down here. So to do that, a very ambitious experiment have been proposed. This is the last one over a suite of experiments. People from here are involved with actually this proposal and thinking about this experiment. No, not that prism. Probably at the end of the day, it won't be this one. It will be something else. Technologically, it's something very challenging to do. So let me conclude. This spring, it was going around Twitter and the local network that the universe is a maximally boring universe. After the announcement of the Planck result, we look for deviation from the lambda CDM, and we haven't found any. The standard cosmological model has survived in even more stringent tests, and deviation from it are even more constrained. But eventually, something will have to give, because the model is incomplete. We have a framework for inflation, but we don't have a theory of inflation. We know that neutrinos have non-zero mass, and we know that neutrino masses give an imprint in the cosmos. The point is how much smaller, while in the lambda CDM model we just typically put neutrino mass to 0. The point is how much smaller would the observational error bars have to be before something has got to give. And one take-home message, for example, is that neutrino mass is within the reach of the next generation of experiment of larger scale structure. So let me conclude. Precision cosmology means to try to go from what to why and try to address the fundamental physics question, example neutrino, initial condition, energy, but this is extremely challenging. And it's also important to keep in mind that from the precision era, maybe we should go to the accuracy era. It's good to have small error bars, but you want that the true value is within your error bars. You want, for the statistician among you, coverage. Large ongoing and future galaxy survey cover a large fraction of the observable universe. It's driven by dark energy study, but there is much more. So for example, the Euclid mission that I mentioned can be considered one of these ultimate experiments for the large-scale structure. It will basically observe almost all there is to see. CMB polarization is a window in the early universe and into new physics high energy. And I'll stop here. Thank you.